Okay, welcome to Lesson 10 of Module 4. This is titled A Critical Look at Proportional Relationships. So we've been doing linear equations. We've been looking at linear equations in one variable and solving them, classifying the solutions. We've done quite a lot with that. And we're going to continue in this lesson to look at how proportional relationships play out in linear equations. So let's look at this first example. Paul can walk 2 miles in 25 minutes. How many miles can Paul walk in 137.5 minutes? So we have a proportional relationship. We're assuming that if he can walk 2 miles in 25 minutes, then in 50 minutes, he could walk 4 miles. And so on. So think about how many miles could he go in 75 minutes. You could pause it and think about it and come back. So in 75 minutes, 75 is 3 times as much as 25. And so he could go 3 times as far. He could go 2 times 3 or 6 miles. So what about 100 and 125? Well, in 100 miles, he could go 4 times. 4 times 2 is 8. And 125 is 5 times 25. So 5 times 2 would be 10. Okay, so our table is getting us closer to an answer, but we're not quite there yet. So think about, how would you set this problem up to find out how many miles Paul could walk in 137.5 minutes? Okay, so go ahead and pause it and come back, and I'll show you one way you might use. So because this is a proportional relationship, in other words, every 25 minutes he's going the same distance, I could set this up as a proportion. So I could say if he goes 2 miles in 25 minutes, then he can go some number, we'll call it X miles, in 137.5 minutes. Okay, so what I'm left to do is to solve this equation for X. And I'm not going to review it, but we have seen and talked about, even back in lesson 8, I believe, that if 2 ratios like this are set equal to one another, then their cross products are equal. So I have a new equation when I do this, and I have the equation 25x, or 25 times x, is equal to 2 times 137.5. Whoops. 0.5. Okay. So now all that's left to do is to solve for x. And so to solve for x, I need to divide by 25. So my distance, x, in miles, that Paul can walk in 137 minutes is this right here. So I am going to do that. So 2 times 137.5 is 275. And I still have to divide that by 25. So X is equal to, I just need to know how many 25s are in 275. If I want to work it out in my head, it's pretty easy because there are 4 in every 100. So up to 200, that would be 8. And then there's 3 more. So x is 11. 275 divided by 25 is 11. Okay, so that answer makes good sense because, let's get rid of this, because I already have my results for 125 minutes to go 10 miles. If I add another 25, I get 150 minutes and 12 miles. 12 miles. Get this out of the way. So 137.5 is somewhere in between these two, and 11 is in between those two. Okay, so now I'm going to ask myself a different question, and I'm going to say, how many miles, y, can Paul walk in X minutes? Okay, and in my first question was, how many miles can Paul walk in 137.5 minutes? Now I want to be more general. So notice I've got 2 variables. I've got y, which is miles, and x, which is my minutes. Okay, so I already know that Paul can go 2 miles. We're on the same problem here. So he can go 2 miles in 25 minutes. And that is actually his rate. That is his rate that he goes. Now, before we set up a proportion and we said, well, how many miles can he go in 137.5 minutes? Okay, and we set up that proportion and solved and found that it was 11. Okay, so if I want to be more general, what would my proportion look like? Well, it would just say, if I can go 2 miles in 25 minutes, then I can go y miles in x minutes. And those 2 rates will be the same. Okay, we're going to use the same method that we used. Remember, these are like those linear equations in disguise that we did back in lesson 8. Remember, anytime I have 2 fractions or ratios set equal, I know that the cross products are also equal. So this leads to a different equation that looks like this. It would just be 2 times x, and I know that that's equal to 25 times y. Okay, and now I want to write this as y equals something because I want to know how many miles y Paul can walk in x minutes. So I'm going to take and divide both sides by 25, which is the same as what I did before, and that's going to lead to this equation. So on this side I now just have 1y, and over here I've got 2 25ths times x. So what I have is, get this in a different color, I have y is equal to 2 25ths times x, or y is equal to 800ths, if I want to write it as a decimal, x. Okay, because 2 over 25 is the same as 8 over 100, and in fact that's one of the ratios that was on the table that we made on the first page. Okay, so these equations right here will allow us to figure out the number of miles that Paul can walk in any number of minutes just by putting in numbers. So I could have used this equation with my 137.5, or if I want to know for any other number of minutes or number of miles, I can solve for the other variable. Okay, so this would be an equation in two variables. All right, let's look at another example. Okay, consider the following word problem. Alexa walked from the Grand Central Station on 42nd Street to Penn Station on 7th Avenue. The total distance traveled was 1.1 miles. If it took Alexa 25 minutes to make the walk, how many miles did she walk in the first 10 minutes? Okay, so take a couple minutes and see if you can come up with something for that. And this you do not have in your notes. Okay, so just use a blank sheet of your paper there. Okay, so you might think to use a proportion for this, and we can set up that proportion by saying she went 1.1 miles in 25 minutes, so she could go some number of miles in 10 minutes. All right, so I would set those cross products equal, so I would have 25y is equal to 10 times 1.1, which would be 11. And then continuing, I would divide by 25 and get y is equal to 11 25ths, which I'm going to rewrite as 44 hundredths. I can see that multiplying top and bottom by 4, so it would be 44 hundredths. So it would be 0.44 miles. So she could have gone 0.44 miles in the first 10 minutes. Okay, so we could do that. But let's continue reading about this problem. What if you have more information about her walk? She walked from Grand Central Station along 42nd Street to an ATM machine 3/10 of a mile away in 8 minutes. It took her 2 minutes to get some money out of the machine. Okay, so do you still think your answer is correct? Or do you think the answer that I came up with there is correct? Well, obviously it's not, because with this additional information that we have here, in the first 10 minutes, she had only gone 3/10 of a mile, not 0.44. Okay, so we have to think about what's going on here. Why is that the case? Why didn't she get as far as we thought she would? And the answer is that she's not walking at a constant rate. She's being normal. Normally, we would not walk at a constant rate. We would go, maybe part of the journey we'd be walking quickly, the other part we might be walking slowly, and like we see here, she even stopped for part of the time to get some money out of a machine. So she's not walking at constant speed. So let's see what that does. Okay, so here's more details. She reached the 7th Avenue Junction 13 minutes after she left Grand Central Station, a distance of 6/10 miles. There she met her friend Karen, with whom she talked for 2 minutes. After leaving her friend, she finally got to Penn Station 25 minutes after her walk began. So she did spend 25 minutes walking, and she went a total of 1.1 miles. The difference between this and the first problem is that the first problem assumed constant speed, that her speed was the same over the entire trip. So here's a chart that kind of shows what she did. So in the first 8 minutes, she went 0.3 miles, 3/10 of a mile. This part of the journey, between 8 and 10 minutes, she didn't go any further because she was at the ATM. This is where she was at the ATM. And then she went another 3/10 of a mile in the next 3 minutes. So from 10 to 13 minutes, she traveled some more. And then, if you remember from the story, she spent 2 minutes talking. So she didn't move any further. So she's still at 6/10 of a mile. And then in the last 10 minutes here, she went the last little bit of the trip and made it all the way to 1.1 miles in 25 minutes. Okay, so you can see from this chart, it's not like the first one. It's not regular. She's not moving the entire time, and she's moving at different speeds on parts of the journey. Okay, but what we can do is find Alexa's average speed, and her average speed, her average speed is, and you can write this down, this is average speed is total distance traveled divided by total time. Okay, so her total distance was 1.1 miles, and she did that in 25 minutes. So that is her speed, 1.1 miles in 25 minutes. And if we assumed that on every time interval she went the same constant speed, then if her average speed was the same over all those time intervals, then we would call that constant speed. So if we assume constant speed for Alexa's journey, we would have what we started with, which was 1.1 over 25. This is miles in minutes. We could say that is constant. That is her speed over the entire trip. And we wanted to know how many miles in 10 minutes, and we would assume that that is the same constant there. So that's why we could write a proportion like you may have done and like I did in that opening part of this example. So if these are both equal to a constant over any interval in her trip, then I could set y over 10 equal to 1.1 over 25. And that led to a distance of 0.44 miles in 10 minutes. Okay, so what if we wanted just a general number of miles in any number of minutes? Then let's get rid of this, because this was specifically for 10 minutes. Instead of y over 10, I would have that she could go y miles in x minutes. And that would be equal to the constant, like we have stated here. Okay, so then I would have y over x is equal to 1.1 over 25, which leads to y times 25 is equal to x times 1.1. And then I will divide by 25 and get that y is equal to this fraction right here times x. 1.1 over 25 times x. And x is y is distance and x is time. Distance traveled and time to use. So this would be a general equation that could be used for any amount of time to find the distance that it would take for any amount of time to go on that journey. Okay. So the point of this example is to realize that unless we assume constant speed, where we have the distance and time for any interval being the same constant, no matter if my interval is 25 minutes or 10 minutes or x minutes, I'm assuming that these are equal to the same constant the whole way through. So I can write this proportion only because I'm assuming constant speed. So the whole point of this was to say if a problem does not say that a person is traveling at constant speed, then they probably aren't. And sometimes in using math, it's helpful even though we know that somebody or something is not traveling at constant speed, we can, for the most part, assume that they are because it's close. So more realistic is Alexa's journey, where she went faster and slower and sometimes stopped. But most of the problems that we do are going to assume constant speed. Just make sure that the problem says that. All right, now we're going to take a look at the first two exercises. If you'd like and you're feeling confident, you could work on exercise 1 and 2 and then come back and check your work. Otherwise, you can check your work as you go along. But do think about these problems and not just listen to me do them, right? You got to think about them first and then listen to the video. Okay, so pause as you need to. And I'm just going to go ahead and go through and work these problems out. Okay, so Wesley walks at a constant speed from his house to school 1.5 miles away. It took him 25 minutes to get to school. What fraction represents his constant speed, C? Well, his speed is going to be his distance divided by his time. So it's going to be 1.5 miles over 25 minutes. And if I simplified this, I would have that the number of miles per minute that Wesley can walk. Okay, so that's part A. This exercise has several parts, but that's because it's walking you through this process. Okay, so part B says you want to know how many miles he has walked after 15 minutes. Let y represent the distance he traveled after 15 minutes of walking at the given constant speed. Write a fraction that represents the constant speed in terms of y. Okay, so once again, our constant speed is the distance over the time. So y is representing the distance he traveled in 15 minutes. So y is my distance, and my time is 15 minutes. Okay, so now part C says use the fractions from part A and B to write as a proportion to solve to find how many miles Wesley walked after 15 minutes. Okay, so we've got these two fractions here and here. They're both equal to the same constant speed because we're assuming that Wesley walks at a constant speed from his house to school. Okay, so part C asks us to write the fractions from parts A and B as a proportion and solve to find how many miles Wesley walked after 15 minutes. Okay. Okay, so for part C, you should have a proportion that looks like this. 1.5 miles over 25 is equal to y over 15. Y is the miles traveled, and we want to know how many miles that would be in 15 minutes. So obviously it's going to be less than 1.5, but how much less? So in order to find out, we can do the math here by doing the cross products like that. So our new equation would look like this. It would be y times 25, or 25 times y, is equal to 15 times 1.5. All right, so I'm going to work this out. So 25y is equal to 22.5, I believe. All right, so now I can divide both sides by 25 in order to get y by itself. And I'm left with, on the left-hand side, I'm left with just y. And on the right-hand side, when I do that division, I get 0.9, or 9/10 of a mile. Okay, so he can go 9/10 of a mile in 15 minutes, which does seem to check out. It's less than 1.5. It's more than half of it, though. 15 is more than half of the trip. So you can do a lot of number sense stuff just to double check your answers on problems like this. Okay, so now here's the general case in D. We're going to let y, now notice they're defining the variable for us. Let y be the distance in miles that Wesley traveled after X minutes. So we're letting y be the distance, and we're letting X be the time that it took. Okay, so I can do the same thing because I know that y, whoops, wrong pen. Y is distance, so we've got y over x would be the ratio. That would have to be equal to that constant speed again. Okay, so we've first written that ratio, but what is that constant speed? It's the same as before. So we have y over x equal to 1.5 over 25. Okay, and then solving, I get 25y, using the cross products, is equal to 1.5x. I'm going to divide by 25, and I get that y is equal to 1.5 over 25 times x. All right, let's look at exercise 2 now. And again, you could work ahead on this one and then come back and turn the video back on and check your work. Okay, so Stephanie drove at a constant speed from her apartment to her friend's house 20 miles away. It took her 45 minutes to reach her destination. What fraction represents her constant speed? So we've got her constant speed is the distance over the time. So she did 20 miles in 45 minutes. Okay, so that fraction represents her constant speed. Okay, part B here asks, what fraction represents constant speed if it takes her X number of minutes to get halfway to her friend's house? So again, our speed is going to be distance over time. Our constant speed will be distance over time. So we need to know the distance and the time, the elapsed time, how much time it took. Well, the distance is halfway to the friend's house, so that's going to be 10 miles, right? It's going to be 10 miles because that's halfway to the friend's house, and the friend's house is 20 miles away. Okay, so the time is what I don't know. The time I can solve for is X. The time is X number of minutes. So it's going to be X minutes here. Okay, so I can write that fraction now because my constant speed is going to be the distance, which is 10, over the time, which is X. Okay. So now I'm going to use what I had from parts A and B to do C here. So C says write a proportion using the fractions from part A and B to determine how many minutes it takes her to get to the halfway point. So the halfway point is 10. So in that first part, I had that C was equal to 20 miles in 45 minutes, and that was my constant rate there. So because these are both equal to the same constant rate, I know they're equal to each other. So 10 over X can be said equal to 20 over 45. Okay, I want you to look at that, maybe you have already, and see if this proportion could maybe be solved directly. We can certainly solve it by doing cross products, but we can also solve it directly. So go ahead and pause the video and see what you think about that. Okay, so this is the proportion we're talking about. And what you might notice is that this one we're going to be able to do maybe even in our heads. I can see that 10 is half of 20. So to make these two fractions equal or equivalent, then whatever X is should be half of 45. So that's how we find equivalent fractions. So I can jump straight to that X is equal to X is 22.5 because it has to be half of 45 in order for these to be equivalent fractions here. So what does that tell me? I know X is, in this problem, determined, it's X number of minutes, 22.5 minutes. Okay, so part D again wants this two-variable equation to represent how many miles Stephanie can drive over any time interval. So we need to define some variables. So we're going to let y equals the distance traveled, and x will let be the time time it takes to run that. Okay, so the time it takes. And so I can write my constant speed yet another way, that it is the distance traveled over the time it takes, y over x. So I have y over x. So now I can write my equation because I've got y over x is equal to, either of those proportions will work. Equals 20 over 45. Okay, and simplifying that out, I get that 45y is equal to 20x, and so y is equal to 20/45 x. Okay, exercise 3 you have in your notes, but before we get to that chart in your notes, I'm going to give you some background on this problem and we'll see how the equation was set up for you, and then you can work out the table on that. So Dave lives 15 miles from town A. He's driving at a constant speed of 50 miles per hour from his home away from the city. So in the opposite direction of the city. How far away is Dave from the town after X hours of driving? Okay, so in situations like this, sometimes it's helpful to draw a picture. So we've got, you might try drawing a picture, pause it, and then see how yours matches up with mine. So let's call this town A. And Dave's driving in this direction because he's going away from the city. Okay, and so he lives 15 miles from town A. So let's say this is D for where Dave lives. Okay, and this is 15 miles. So that's where he lives, and he's traveling 50 miles per hour away from the city. So we could say he's out here somewhere. And we're going to define some variables here. We already have one variable defined for us. And let's just underline this question. How far away is Dave from the town after X hours of driving? So let X be hours driving. Okay, then we're going to let Y be what they ask us here in the problem. How far away is Dave from the town after driving for X hours? Let Y be the distance from town. Okay. Okay, so because Dave is traveling in a direction like this, away from his house and away from the train, away from the town, we would say that this would be the distance traveled. But Y is our distance from town. So the distance, how can we write the distance from... Oops. Didn't pick the eraser. Okay, so sorry, let's go on with that. So the y is the distance from town. The distance he travels in a certain number of minutes. The distance traveled is only this part right here. Okay? So if he is y miles from town, so in other words, if this whole distance here from here to here is y, then the amount he actually traveled is y minus 15. So his distance traveled is y minus 15. Okay, so we're going to have to remember those. Hopefully you have those written down because we're going to use them on the next page here for a minute. So x is our hours driving, y is the distance from town, but the distance he travels is actually y minus 15. Okay. Okay, so we've got our variables labeled here. Y is the distance from town. So the distance traveled, we said, would be y minus 15 because he's already got, in essence, a 15-mile head start. And the time is x. So we're driving for x hours. So this would be in hours. The distances are in miles. Okay, so we want to know how many miles Dave is from town, and that's y, after driving for x hours. So we're going to have to write a proportion. So our distance traveled, our speed is going to be the distance traveled, which is y minus 15, over the time it took to do that in hours, which is x. Okay, and we know that that's equal to his constant speed, but the problem gives us his constant speed. It said that was 50 miles per hour, so I can fill that in right now. So I'm going to put some parentheses here just so we don't lose that. Remember, this is actually 50, can be thought of as 50 over 1, doesn't change the value at all. So I can do cross products. So let's look at what that is going to look like here. So 50 times x is equal to y minus 15 times 1. Okay, so I want to, since I'm solving for the distance, y, I'm going to rearrange this equation a little bit. So if I add 15 to both sides, then I get a new equivalent equation that would be, I'm going to flip-flop them around, that would be y is equal to 50x plus 15. Okay, so this equation right here at the bottom, the one we rearranged it came up with, can be used to find the distance from town for any amount of time that this person traveled. So here I've got 50 miles per hour times the time plus 15. Okay, adding 15 means since I started with a head start, if I want to know how far I am from town, I have to always add that 15 back on. Okay, so this leads right into exercise 3 that you have the table for. So let's look at that now. All right, so here's exercise 3. There's that equation that we just gave some background on, that Dave lives 15 miles from town, so that leads to this equation looking a little differently. We're going to correct one thing on here though, because y is not the distance that Dave travels. Remember that y is the variable y is Dave's distance from town. So once again, the y is his distance from town after traveling for X hours at 50 miles per hour. Okay, so we can use this equation to complete the table. And we're going to do it for 1 hour, and 2 hours, 3 hours, 3.5, and 4.1. And we're going to do it by just putting in the value for X. So the first one is done for us. So after traveling 1 hour, Dave is 65 miles from town, because he went 50 miles and he was already 15 miles away. Okay, so for 2, I would have y is equal to 50. You should pause the video and do this on your own. And so this would be 115 miles from town, and so on. So pause it and then come back and check. Okay, so here's the rest of the table filled in. So I've just taken the number of hours traveled, put it into the linear equation, and done the math, and then used it to find the number of miles that Dave is from the town. Okay, in the next lesson we'll be using tables like this, and we're going to start graphing. So you might want to make sure you have some graph paper for lesson 11. Okay, so let's just do a quick recap of what we talked about in this lesson. Okay, so the lesson summary is on the problem set page. So we talked about average speed, and we talked about how average speed is the total distance traveled in a given time interval. So it is the total distance divided by time. Okay, and then we tried to generalize it. So we said if y is the total distance traveled in a given time interval x, then y over x would be the average speed. And when we set that, use that with some of the data that we had in a given problem, then we could write these equations. So if we assume the same average speed over any time interval, then we have constant speed. And so remember, we looked at an example that was not constant speed, but the other examples that we did specified that it was constant speed. So that means the average speed is the same over any time interval. So we can use it to express a linear equation. So if we've got y over x is equal to c, where c is a constant, I'm reading right here, then we have constant speed, and we can write this equation, this linear equation, in 2 variables. Okay, so you're going to be working on the problem set. Be sure to check your work as you go along so that you can be sure that you are getting it. And let me know if you have any problems with that. Okay, and I'll see you back here for lesson 11.